All right, so this is Chapter 7, Section 3, Trigonometric Equations. Our first learning objective is to solve equations involving a single trigonometric function. So we want to know whether theta equals pi over 4 is a solution of 2 sine theta plus root 2. So what we do is we plug in pi over 4 for sine, and we know that the sine of pi over 4 is root 2 over 2. Multiply that by the 2, and we get root 2 plus root 2. That's equal to 2 root 2 and not 0, so it is not a solution. Now we're going to check to see if 5 pi over 4 is a solution. 5 pi over 4, when I take the sine of it, is negative root 2 over 2. And then when I multiply that by 2, I get negative root 2. I add that to root 2 and I get 0. So it is a solution. So we're going to do the same thing with this cosine. Give a general formula for all solutions. List 8 of the solutions. Okay, so when your domain is not restricted, because cosine is cyclical, so when you solve for theta, it's going to hit the cosine periodically. So we're going to give a general formula, and then it's asking for us to list 8 specific ones. So when I add root 3 to both sides, and I divide by 2, so I get cosine of theta equals root 3 over 2. So we need to find all the places where cosine of theta is equal to root 3 over 2. When we look at our unit circle, there are 2 answers, one in quadrant 1 and one in quadrant 4. So it exists at pi over 6 and at 11 pi over 6. And then because cosine has a period of 2 pi, we're going to say k is an integer. So theta is equal to pi over 6 plus 2k pi, or 11 pi over 6 plus 2k pi. And this value here is because cosine has a period of 2 pi. K is going to be an integer. So it's either going to bump you up 1, 2, 3, 4. Any iteration is going to take you back to the terminal angles. So now they're asking, so that's the general formula. Now they're going to ask for us to list 8 of the solutions. So pi over 6 and 11 pi over 6. If k is equal to negative 1, it's going to bump us back 1 whole rotation, so it's going to be negative 11 pi over 6 and negative pi over 6. When k is 0, we got pi over 6, 11 pi over 6. When k is 1, 13 pi over 6 and 23 pi over 6. When k is 2, 25 pi over 6 and 35 pi over 6. We're just adding 2 pi and then whatever integer k value we pick. All right, so let's check out this equation. This one does give us an interval from 0 to 2 pi. So when you have an interval, you don't have to make up a general equation to count for all the cycles. So we're going to add 1 to both sides, divide by 2. So I'm going to plus 1 to get 2 cosine 2 theta equals 1. And then I'm going to divide by 2 to get cosine 2 theta equals 1/2. Then on the interval, I'm going to find the cosine of the angle that is 1/2. So we look at our little chart. I printed out a unit circle. The cosine of theta is 1/2 at pi over 3 or 5 pi over 3. So 2 theta equals pi over 3 or 2 theta equals 5 pi over 3. So once you solve the cosine part of it, you then have 2 times your angle equaling that amount. So how are we going to find the true angle? Divide it by 2. So we are so since this 2 theta doubles our period, we have to account for the cosine of 2 theta equaling 1/2 twice between 0 and 2 pi. So we have it here, 2 theta equals pi over 3, and 2 theta equals pi over 3 plus the 2 pi, because it'll cycle through twice. Thanks, Omega. So the answers are pi over 6, because pi over 3 divided by 2 is pi over 6. Pi over 3 plus 2 pi is 5 pi over 3. And then you divide that by 2, it's 5 pi over 6. Then we got 5 pi over 3 divided by 2 gives us, I lost it for a minute, 5 pi over 6. This is 7 pi over 6. Okay, so this divided by 2 is 7 pi over 6. 5 pi over 3 divided by 2 is 5 pi over 6. 2 theta equals 5 pi over 3 plus 2 pi gives us 11 pi over 6. All right, so once we get out all of our solutions, we know we have them all accounted for. Okay, so my suggestion is after you algebraically solve for it, go ahead and graph it so that you make sure you scoop up all those solutions. So if we had root 3 tan theta, or tan of 3 theta plus 1 equals 0, we subtract 1 from both sides, divide by root 3. We look at our unit circle and try to find what are all the angles that give me a output of negative 1 over root 3. It may not show up as negative 1 over root 3 on your unit circle. It may show up as negative root 3 over 3 if they rationalize the denominator. So when we look at our unit circle, that happens at 5 pi over 6 and 11 pi over 6. We know that 3 theta equals 5 pi over 6 and 3 theta equals 11 pi over 6.
On the unit circle, it says that it's...
Since we divide by 3, adding 2 pi and 4 pi, so the number of times we cycle through triples. So we not only have to add 2 pi, but we have to add 4 pi, so that we'll pick up all the solutions for theta between that interval from 0 to 2 pi. If this part is confusing to you, go ahead and graph it and make sure, getting those two, really good, really easy to get the first couple, which would be 5 pi over 18, because we divide that by 3. And then make sure you get the other ones that are hanging out there. So we get 5 pi over 18, 11 pi over 18, then we add 2 pi to that, 17 pi over 18, 23 pi over 18, 29 pi over 18, and 35 pi over 18. We have to include all those solutions between 0 and 2 pi. All right, so now we have a little phase shift here. We want to know cosine theta minus pi over 4 equals 1. So we're going to find all the solutions where cosine is equal to 1. That happens when theta equals 0. Since 2 pi is not included, it doesn't happen at 2 pi. So we got theta minus pi over 4 equals 0. We add the pi over 4 to both sides, and we get theta equals pi over 4. All right, we can also use our calculator to do the same thing. If we're trying to solve cosine theta equals 0.2, we go inverse cos of 0.2, and we get approximately 1.37. We are on the interval. Inverse cosine, the calculator will only give you an angle from 0 to pi. There is another angle in the interval from 0 to 2 pi. So that's why we got to go. The second answer is 2 pi minus 1.37. So it's that because cosine is positive in quadrant 1 and quadrant 4, we have to work smarter than the calculator and find that second angle that has that solution. So when we're dealing with cos, take your answer and subtract it from 2 pi to find your second angle. And you can also verify this by graphing. If we get a trig function in quadratic form, we are going to let cosine theta equal, you can let cosine theta equal x, and we know how to solve 2x squared minus x minus 1. So you approach it just like you would an Algebra 1 problem. Factor it out. Set each section equal to 0. And we get cosine theta equals negative 1/2, or cosine theta equals 1. From our unit circle, we know cosine theta equals negative 1/2 at 2 pi over 3, 4 pi over 3, and we know cosine theta equals 1 at 0. We're going to solve trigonometric functions using identities. If you forgot your identities or don't know where they are in your notes, flip to the back page of your book. They are all right there. So if we get sine squared minus sine theta equals cosine squared, I can replace cosine squared theta with 1 minus sine squared theta. Then I have a nice quadratic function that I can factor and solve it just the way we did the previous problem. When is sine theta equal negative 1/2? That's 7 pi over 6 and 11 pi over 6. And when is sine theta equal to 1? That's at pi over 2.